Okay, so good morning everyone, and today we are going to discuss about our next topic after our discussion on double slit experiment in our last class, and we are taking this online video lectures because most of the students are actually at hostel and outside the campus. So, just to give you a brief summary of what actually we did earlier in order to make a continuation for with the today's lecture, let me just briefly discuss about the interference effect of light, and we discussed about what happens if we have, let us say, 2 point sources S1 and S2, and if they are localized in let us say they are localized in space. What will happen is, we actually have in our previous class we showed that. So, if we want to find out what would be the contours of equal phase, or in other words what would be the fringes in 3 dimensional space, we can actually see that it would be like a 3 dimensional hyperaboloids of revolution along this axis, and it would be like this. And then if you make a revolution of this structure, then you will basically obtain a 3 dimensional surfaces where the phases are remaining constant, and these are also will give you the how the fringes are distributed in 3 dimensional space. And then we can actually take different cross section along different direction, and this we call transverse section. And here, as I mentioned earlier, we would actually see fringes which would be like these, which are basically linear fringes. And if we take a cross section along this plane, or this plane, and along this plane we actually call it the longitudinal section, and there we actually obtain a set of circular fringes, right. And the kind of example that for this transverse section we actually discussed about the Young's double slit experiment, where we have a point source here and we have S1 and S2, and we can actually find out how much path difference are there for a light ray to come to this point P following path 1 and path 2, and we actually found out depending on, let us say, if we define an angle theta, then I can actually find out the maximum minima. For example, we can estimate what would be the path difference. That would be, this is d and this would be your this would be theta. So, it would be d sin theta as m lambda, where you get the maximum, and for minimum we need to get m twice m plus 1 lambda by 2 for let us say bright fringes, and for dark fringes. Now, this is one example that actually giving you the transverse section, and we also talked about a situation when we have the 2 point source. Let us say this is S1 and this is S2, and we take an angle theta here, and if this is d, then in this case we are basically looking at a longitudinal section, and there we also got the similar relations, but we will actually come to this kind of problem when we today's discussion when we talk about the Michelson's interferometer. So, let me erase this part of the board. Now, in order to get this kind of examples for interference or the circular fringes or longitudinal section, basically design some kind of interference setup where we have, let us say, a point source. Here, for the time being, let us consider for a point source, but the kind of experiment or the interference effect that we are discussing now will also be applied for extended source. But if we consider only a point source, and let us say this is a light ray, and we consider a object here, which I think I will discuss it what it is. It is called the beam splitter. And this is what I am actually discussing now. Let me write it down. It is actually the Michelson's interferometer. What happens is, suppose we have an object called beam splitter. I will discuss a little bit about this, how a beam splitter works. And then the effect of these object is that when a light ray falls on top of it, on the surface of it, it actually some part of it get reflected and some part of it get some part of it get reflected and some part of it get transmitted. It can be, for example, it can be 50% both side, it can be 30%, 70% both side, so that the total intensity remains constant, and there are ways to realize different kind of beam splitter. Now, what happens is, let us say this is a point source and the light actually incident on this beam splitter and it is transmitted, and then we place a mirror here, and this mirror will reflect the light back, and then what will happen is, so this light ray will again get reflected to this direction, and so that we basically see we come up to this point, let us say point A, and then it gets reflected here and it is coming back here. And now, let us consider the other path where the light ray actually taken this path and got reflected, and then we placed a mirror here. Let us call it this one as M1 and this one as M2, and the effect of this mirror would be, there would be another reflection, and this reflected light will again get transmitted back. So, there would be now two beam, and you can actually see that the two path, unlike this experiment where the two path was actually very close by, right, here actually the two paths are completely, they are highly separated, and as a result there is actually a lot of application that we can actually think about utilizing the separation between these two path. Here you do not have that opportunity, but here you have the two path which are separated, and you can actually modify the path individually, and you can do many other things which can actually lead to different kind of applications. So, let me now briefly discuss what this beam splitter is actually. So, let me, before we go to what happens to this interference experiment, let me just briefly describe what this beam splitter is. So, the beam splitter is actually, we can think about one kind of beam splitter. There could be many other different varieties of beam splitters available, but we can think about one simple kind of beam splitter where we have a parallel, let us say, so like a glass plate, and then at the other surface, this surface. So, there are two surfaces, 1 and 2, and the other surfaces we actually deposit silver, and so that it basically become can call it a semi silvered surface. And what happens is, so the light when it actually gets incident into this, there will be a transmission, and this transmission we can actually understand by there will be a refraction, and after this refraction this bottom surface it is semi silvered, that means it has let us say 50% reflectivity. Reflectivity means if I shine let us say the intensity of light with 100 unit with the correct unit, and I will get 50% reflected, 50% get transmitted. And so after this reflection what happens is there would be a reflection, after this transmission there would be a reflection here, and after here it will actually again refracted and go back go to this direction, while this beam which was refracted it actually transmitted through the whole thing, and there would be a displacement here. So, there will be two paths. So, it can be let us say 50%, 50%. For example, if I start with a amplitude of light with A, this beam will have an amplitude of A by root 2, and this will also have amplitude of A by root 2. So, this is I think one kind of beam splitter. There could be other kinds of beam splitter which are like, for example, if you think about, so this is one, this is another kind of beam splitter where you basically it is like a cube, and at the body diagonal there is a, you can actually make some deposition here, and that can also behave like a cube beam splitter. So, this material at the interface between these two, so the light will get reflected and there will be a transmission like this. So, this is another kind of beam splitter, and different kind of beam splitter can have different kind of properties, and we will briefly discuss when we talk about the result of this Michelson's interferometer. So, now let us come back to this Michelson interferometer. Let us just clear this space, and then what you now can see that we considered a point source, but I also said that it can also work with a extended object. So, although we considered a point from the extended object, this can actually be an extended light source. And from this extended light source I can actually get a light ray here which is getting reflected, and let me, since I talked about the beam splitter, let me just draw it a little bit properly. Maybe I can use a different color now. And the light which will get transmitted, we can take another color. Now, this light ray will actually get reflected, and it will follow the same path like this, and then it gets transmitted, whereas this beam which is getting reflected will actually also have a reflection here. So, now if you see that up to this point for all these two beam. So, this let us say we can now think about two different paths. So, let us say path 1 and path 2 up to this point they actually have the same path, and then from there they actually you can actually control by putting a separation between from this point to this point, let us say for or from a center of this beam splitter to this point, let us say this is L1 and you put it L2, and you can see that the light from here will actually come here and then get reflected. So, it would be twice L1. So, total path that is actually traveled by the light, and then for this path it would be twice L2. That means, the path difference between these two would actually be twice, let us say L1 minus L2, or we can think about twice D if we make this L1 minus L2 to be D. And then we can now see that, so these two beam are actually a parallel ray, kind of parallel ray, right. So, actually they are coming it's like a parallel. That means, if we now we can think, so actually we in order to see the fringes, unlike this experiment where we can actually place a place a screen here and observe the fringes. Here what happens, if we place a screen here at a finite distance, these two ray may not actually come together, right. So, this could be a parallel beam. We will actually see by another drawing that why these are actually are parallel beams, and in order to see that we basically need a arrangement, or let us say lens, or you can call it an objective lens, or objective, or you can also call it a telescope. So, what telescope does is that it actually it helps you to see things which are at infinite. So, these fringes in fact they will actually form, they are actually localized at infinite distance. So, that is why we need a lens, and this point that I am actually trying to make here would be clearer when I will draw the equivalent picture of this by considering what happens. Suppose if we observe from this point, we can actually cannot trace back these two different paths, right. So, would basically appear that the light ray is actually coming from same direction, right. So, in other words, we can actually draw a similar picture which is equivalent. So, this is this point from, let us say this is just a straight line, and we can draw these two mirror, as I said that if I look from here, then it would be as if the two mirrors are in parallel, right. So, I can think about placing a mirror here, and then let us say what happens to an source. If I place a source here, let us say S, and this source we know that it will actually make a reflection for this mirror, it should be at equal distance. So, if I draw it roughly tie approximation, this distances, keeping this distances same. So, this would be let us say S1, the reflection, the image of this point, and then the another mirror which is separated by distance L1 minus L2 or by D. So, let us put another mirror which is at a distance D. Then what happens? So, again we need to draw the same thing, we basically need to see what equal distance it can actually can corresponds to. So, it would be around here and it would be S2. So, there are two images corresponds to these two different mirror M1 and M2, and if this is D, so you can actually clearly see that this would be 2D, right. Now, what happens? Now, this picture and the picture that I just now erased, now this is actually equivalent to our previous picture, it is just very similar to whatever we are looking at is the longitudinal section. And in order to again get how basically the fringe will actually look like, now you can actually see that this would be circular fringes here, and the reason and how we actually observe these fringes, right. So, let me now see what happens if we consider a ray coming at angle theta, right. Actually the source is here. So, these are virtual images. So, it would be like, let us say this point, the light is coming here, and then so this would be, let us say, one beam, and this angle is theta, right, and we take another point So, now you see that these two rays are actually indeed they are actually parallel, and they will actually not meet at a finite distance. So, there is no way that you can actually get the fringes all over, and that is why I call it these fringes are actually localized at infinite. In order to see that, what we do is we actually take a lens and we collect this ray such that, so this is the center of the lens, and if I now define the focal plane here, focal plane is at a distance, let us say d. Now, what happens at the focal plane is that you put any parallel ray, it will actually make a point. Now, since this is not parallel to this optic axis, what will happen is it will actually focus at a different point rather than this point, and it will actually come to this point, right. And if I now see that if I join these two, this point and this point, right, I can actually, so any ray can actually pass through this and the focal plane. So, it would be like this, right. So, this is the principle that we use when we do the ray diagram for a lens, and then if you see that this is theta, this is and these are parallel. So, this theta and this theta are same. That means, whatever actually we discussed in our previous class about two sources S1, S2, and we actually, so in this case please try to see the difference between the Michelson's interferometer here and two localized point source here. The only difference is that, so you keep the distance d here, and then what you do is you take a theta angle here, and then you can actually see that you do not need to have parallel beams, right. What I am trying to say here, so these ray that you are actually using, they are actually may not be parallel beams, and you can actually get a fringe pattern at any point here, just like as long as it is all over 3 dimensional space. But here it is actually forming at infinity, because they are the setup is such that the rays that are coming, it is as if the rays are coming from infinity, and that is, I think, the difference here. And you can actually use all the everything that we discussed for this problem to this problem, except that now this would be your distance, this would be your, let us say, the distance of the mth fringes from this point, and we can now let me so we can actually now find out what happens to the condition for maxima or the bright fringe and the dark fringes. Okay. So, let me just erase these points. So, I think let us try to see what happens here. So, if this is d, then if this is theta, then we can see that. So, this is your the condition would be. So, this part is the path difference between the two. So, d would be your, for this problem, please remember that this is, we are doing it for this problem, and then we will use this one here, we will apply it here. And so, here d would be your m 0 lambda. So, since at this point if we look at theta equal to 0, then this would be your the order of the central fringe m 0, which is here it is bright, right. And then what happens is d cos theta at non-zero theta, basically this is the path difference would be this much, and if this is theta, this would be your d cos theta, and d cos theta would be your m lambda. And then for small angle theta approximation, we can actually expand this term to 1 minus, and let us put it theta m, since we are talking about the mth order fringe, theta m square by 2 as m lambda. And if we use this, then we can actually get d theta m square by 2 as m 0 minus m lambda, or n times lambda, right. And however, theta m is your, let us say I can call it r m, or r is the radius of the fringe, would be your, if this distance is d, then your r m would be your theta times d, theta m times d, right. So, your theta m would be your r m by d. Okay. So, this just a conversion from the radius of the fringe to the angle of the mth fringe, and we can use this here. So, in other words, we can actually write, let us say theta m is r m square by d square would be your twice n lambda by d, right. That means your r m squared would be d square twice n lambda by d. So, this I think we already got it in our previous class, but again we actually re-derived just to recap, and then we will actually use it here. So, here for example, here this is theta, and we know the relation. So, if instead of using this lens, if we would avoid the use of this lens, then what would have actually happen is this will actually go for a long distance, infinite distance, and you basically get a very large r m, but that is actually not so it is not generally done. So, we use a lens here, but this angle is theta, and if we actually find out, then actually we so this, for example, this would be actually still be valid there even if we do not use the lens. So, we are good even if we do not use the lens up to here, and then if we use the lens, then what will happen is we basically have to consider the distance from here to here d, and so this distance d is actually the distance from here to here, just to get the theta m. Instead of theta m, we, in order to eliminate, or in order to find out the radius, and the relation between the theta, right. So, if I use it here, So, then here you see that d here is actually, so if I make the distance between the two mirrors small d, then actual separation between the, or difference between the path would be 2d. So, here if I want to use this formula, for this it would be like r m square, which would be d square n lambda by d. This is for this geometry. Okay. And now you can see that we can use this formula and find out different, we can actually apply it and get different kind of information. For example, if we in the telescope, if we could measure the radius of these each of the fringes, then we can actually find out. Is there any question? Okay. How much time I have? 25 minutes remaining. Oh, I have a lot of time. So, I think I was, is it faster? Okay. So, then I think let me now erase this part. Okay, let me keep this part, let me just erase this part of the board. Okay. So, so there are few things that I actually need to consider now. I have not actually talked about. So, if you see that these two rays, so if we use this kind of beam splitter, so let me again come back to this picture, and then again we will discuss different kind of application. So, few points. So, one is, so if we use this kind of beam splitter, then what happens is, if you see that this picture, maybe if it is not visible, maybe I can draw it here in more clarity, a little bit bigger. Now, if you see that, if I just zoomed in this part, and you see that so I think in our very beginning, when we talked about the reflectivity and transmittivity, we in reflection coefficient, we actually discussed that when light, or any, this is actually true for any reflection of a wave, there we actually saw that if it is reflected from a denser medium, then you will actually observe a phase difference of pi. And so, this is if this is, let us say, glass, and this is air, then you can actually clearly see that the transmitted wave will actually have no phase difference from the incident wave. However, if you see that, I think I did a, I think it is opposite, right. So, if let me see. So, if the reflectance, yeah, I think it is from rarer to denser, right. Yeah. Or denser, this is fine, right. So, this so this one will have a phase difference of pi. Oh, this is right, half silver mirror. Yeah. Yeah, so this is silver mirror, that's right. Yeah. So sorry, thank you. I think I was not drawing this on the silvered part. Okay, so if this is a silvered mirror, then you can actually see that it will suffer a phase difference of pi.
No, so I think that phase difference when the blue line is going to get reflected. That time.
Oh, oh, I think that is what I was actually confused. Yes, right. So I think so there will not be any phase difference here. So no phase difference here. However, when the light actually comes back and get, so there would be a light which is actually coming from reflection, there it will actually suffer a phase difference of pi. Yeah, I think that is making more sense. So there will be a phase difference of pi and no phase difference, and then what happens is it will again come back, right. It will follow this path and transmit it. So these two, that if you see, so one will have a 0 phase difference, the other one has pi phase difference. As a result, this condition that we actually got here for in the case of this Michelson's interferometer, this would actually give you dark fringe instead of a bright fringe. So if you compare, this one would actually has no phase difference between these two paths. However, in Michelson's interferometer, if we have this kind of beam splitter, please remember. So if we have, for example, if we use a different kind of beam splitter like this, a cube beam splitter, then you would actually do not have that. So you basically come back to the same condition as your earlier case. So there again you will not have the phase difference of pi between these two rays. So if I replace this beam splitter with this, then this condition of dark and condition of bright would be different. And for example, the condition would be for bright, it would be this would be the condition for your bright fringes in case of right. Okay. So in this kind of beam splitter, if we use, this is as a cube so it would be for a cube beam splitter. So let me just erase this part now. So if we use a cube beam splitter, your condition R m square as d square n lambda by d would give you and here also if say that 2 d, if we equate it to m 0 lambda, this would give me the central bright fringe, or the central, actually it would be like a bright spot, and then there would be different fringes, right. So, in this case if we had used a Q beam splitter, then this would be the condition for that central bright maxima. And if we use this kind of beam splitter, then you get, so this condition would give you the central, so twice d as m 0 lambda would give you central dark fringe in case of this. All right. So, this is another thing, and next we actually want to talk about another important thing that I have not mentioned yet, which is actually for this kind of beam splitter we actually have not talked about what happens here. So, we actually see that we only said that up to this point the path for all the rays are same, but that is not correct, because we have not included this part. So, if you see, let me just in the zoomed in view, we can actually see that the ray actually from this point, this ray is actually traveling an extra path here. How much? 5 minutes? Okay. So, I think I will actually conclude this within 5 minutes. So, from this point, if you see that this ray actually have transmitted, and then again while it is coming back, it is following this path. So, it is traveling this distance twice, and if suppose if I make this thickness of this plate, glass plate, very thick, then what will happen is that this path difference introduced by this distance would be very, very large, and as a result what we will actually find that you may not see any fringe if the distances between the two paths are very large, and if suppose it is very thick. In order to avoid, in order to compensate, but this actually is not happening, for this is let us say path 1 and this is path 2. So, path 1 is traveling extra distance, which is given by this kind of beam splitter, and in order to compensate that, basically what you do is you put another beam splitter. So, if I put another beam splitter here at the same angle 45 degree, but this part is not half silvered mirror, then what will happen is this path will also travel, basically it will also do the same thing, right. So, it would actually so, it will also travel same kind of path, and these two paths will then get compensated. So, this way we can actually compensate the extra path that is introduced for path 1 in this, and this is actually important. Otherwise, if we do not put this, then if we make this very thick, then your fringe pattern may not be that much sharp, or the visibility may not be that good. So, in order to compensate, we basically make this one, and this we call a compensator. Okay. So, using this, so the other applications that actually you can think about is, for example, so let us say what happens if we now, let me just discuss two different problems. Let me just now erase this part. Yes, 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 yes.
So there is this factor of 2.
Yeah, yeah. So that I think I mentioned here. I actually mentioned here. Maybe if there was a question, maybe it was missed. Yeah. So I had missed. I had said that. Yes. So the other thing that we can actually do, let's say you use a some way, some arrangement, some micrometer screw to move this mirror little bit. And what you can actually do with this method is that, let's say you have this twice d as m naught lambda. So this is your condition for, let's say, the dark fringe, central dark, for this kind of beam splitter. And sorry, I actually have also used a compensator here, which I just mentioned. So this compensator will not be required if you have a different kind of beam splitter. This is for particularly for this kind of beam splitter. Please remember that. And so what you can now do is that you vary the distance between the mirror by micrometer screw, and you get as a different separation twice d prime, and you get a different order of the fringe m naught prime. And you can actually see that how easily you can find out the wavelength. So you can actually estimate the wavelength. So what is happening here? So if we, let's say, increase the distance d prime, then your order, so if I increase distance d, your order in the center is actually increasing. So if it was m 0th order, it would be a different more than m 0th order, let us say m 0 prime order. And then what you do is, so you have increased this distance, right, or let us say reduce this distance. Then this is a separation between these two different distance delta d. So if I change the mirror by delta d, then the change. So what will happen is, in the fringe system, there the fringes will appear or disappear depending on, if you increase d, then you will see that the fringes are appearing, because your m 0 is actually increasing. But if you reduce the d, then it basically see collapse. And so that way we can actually count how many fringes have appeared and how many fringes are disappeared. And from this number, let us say if we make it 100 of such fringes has appeared with a travel distance of delta d, then I can actually find out what would be lambda very precisely, right. So this is one application. There are other applications. For example, you can as I mentioned that these two paths are highly separated, they actually separated. So you can actually introduce different kind of element here. So I can put a element which is, let us say, a thin transparent film, and very thin in the sense of the order of the wavelength or even smaller. Then you can actually find out by introducing of these film how much fringes has actually appeared, or I think it would be, yeah, it will actually depending on where you are introducing, it will appear or disappear. And by counting the number of such film, you can actually find out how much extra path difference that you have introduced. For example, if this distance is t, then it would be n, which is the refractive index, times t would be the path length that you can actually estimate and find out what would be your thickness of the thin film. So this is another kind of applications that you can actually think about. And you can also think about, let us say you put it in a so you basically put a gas here. Let us say you make a transparent window cylinder, and you make it transparent and you put gas inside, and you can actually measure the refractive index of the gas or how it changes with different pressure. So, if I can increase the pressure of the gas, it can, the effective index can increase or decrease, and that would actually introduce different path difference, and that you can also measure. Okay, so, with this I would like to conclude the Michelson's interferometer, and if you have questions and comments, you can please write to the YouTube link, and we will actually get back to you. Thank you.